Oke, kita mulai. Let's start our lecture today. So please turn on your video so that we can, start our discussion. Okay, welcome to the second meeting. So this is going to be a meeting where we get quite technical on the topic. Today, the topic is going to be the estimation of simple linear regressions. So this is basically the second chapter in Jeffrey Wooldridge book chapter. So I'm hoping that you've had a chance to review it. So I guess since the time is precious, I think we can start. Feel free to unmute yourself and then ask questions, particularly on the concepts that you haven't been able to understand. So don't let a concept go without understanding it. So feel free to unmute and then ask the question. Okay. From time to time, I'm going to provide you with an opportunity to ask questions, just to make sure that everyone is on board with the discussion on hand. Okay, so I'm trying to share screen and do some annotations as well. It may get a bit choppy, I hope not, but I think this is something that I need to try because there are going to be some notes which I think are going to be important for you guys to understand. So let's try for today's meeting. Okay, so basically we have several points of discussion today. We have the definition of the simple regression model. We have derivation of OLS estimates. We have discussions on the goodness of fit as well as functional forms. We're also going to have discussion on the unbiasedness of OLS as well as the variance of OLS estimators. So these are going to be the key topics of the discussions today. I won't go to all the details, technical details of some of the mathematical detail or the statistical detail. And so I'll put those details in the appendix, just in case you guys are interested in looking at the detail and technical derivations and stuff like that, okay? All right, so I'm going to start with the first topic, which is the definition of the simple regression model. Again, the relevant reading for this chapter is the second chapter of Jeffrey Wooldridge, Introductory Econometrics, a Modern Approach. Again, I'm hoping that you guys have already had a chance to review it. If you haven't done so, please spare some time to review the chapter. I think the chapter is really handy and it's really insightful. It's also quite intuitive relative to other econometrics textbook which are available in the market. So please do spend some time to review the material. Okay, so let's get into the motivation. So we discussed last week that there are several questions that we're interested in. So for example, we're interested in the effect of higher parental incomes on student test scores, for example. This is particularly important, especially for households, the poor and the vulnerable households. And so if we supplement them with additional income, will they be able to spare more resources for their kids and so push their kids' learning in school? So that's something that we're interested in. If you guys talked about managerial economics or economics in general, we care about incentive. So one of the topic of incentive that we care about is the effect of incentive on productivity. So we're interested in whether or not higher CEO salaries has an effect on the firm's performance. We're also interested in, for example, questions related to financial loans to improve the profitability of micro and small enterprises. So if you read the literature on poverty and then micro and small businesses, you'll find that one of the key issues that micro and small enterprises face are capital, okay? And so without adequate capital, they won't be able to, create the production that they need, and so to generate the goods and services for their business. And so improving their access to financial loans will allow them to improve their production, their capacity, and so they'll be able to offer more product and then get profits at the end. So these are some interesting questions that we care about, and I'm sure that you guys have interesting questions as well. And so in a couple of slides, I'm going to ask you to think about an interesting questions. It doesn't have to be something that's, very much economics or business. It could be something that you care about, and it'd be interesting to see various questions from everyone in the course. Okay. All right. And so let's start with the simple regression model. And so in the previous question, we're interested in, for example, the effect of parental earnings on or parental incomes on the student test score. Okay, so the parental income is going to be X. Okay, so this is say the parental income, and Y is going to be the student test score. Okay, so in the literature of economics of education, we care about the effects of various of inputs. It could be schooling inputs, it could be family inputs, and the effects on test scores. So parental income is definitely one of the inputs that we care about, and so we want to write it as the following. Okay. In the previous question, we also talked about the effect of CEO salaries. And so this is CEO salaries. And then on the left-hand side, the Y variable, this is the firm's performance. Okay. So performance can be, measured by different measures. It could be the earnings per share. It could be other kind of like performance that we care about, like profitability and stuff like that. So we don't have to be specific, but the idea is there. Okay, so I'm going to go through, bit by bit on the feature of this function. Okay, and so I would just want to remind you that we have the notion of population, and we also have the notion of sample. In this particular case, we start with a population regression function. So in general, when you write a function, you should start with a population regression function, okay? Before later on, we're going to use a sample to try to estimate the parameters of interest, okay? So what we're interested in this model is that we're trying to see how Y varies with changes in X, okay? So that's the main or like the key feature of this model that we care about, okay? Now, as you can see, there are also several descriptions of the model. The first one is the I's, okay? So the I's here indicate the entity, okay? And the entity is going to be dependent on the research questions, okay? So for example, if you care about the effect of parental income, oops, my bad. If you care about the parental income on, say, if you care about the parental income on student test score, then the observation would be at the student level. If you care about the effect of CEO salaries on business performances, then the entity could be the firm. If you care about whether or not financial loans have any effect on businesses, the profitability of the businesses, then the entity that we care about here is small and micro firms. So it really depends on the questions that you're asking. Okay, so just getting into the technical details, Y is going to be referred to as the dependent variable, okay, and then X is going to be referred to as the explanatory variable, okay. So these are some of the definitions that I think it's important for this particular simple regression function. Any question up to this point before I continue?
Sir, can I ask?
Sure, go ahead.
How can we differentiate between the dependent variable, independent variable, explained variable, and All the variables, sir. I'm just curious about that. Thank you.
So dependent variable is another name for explained variable or the left-hand side variable. Independent variable is going to be another name for explanatory variable or control variable. Some people call it the right-hand side variable. And so these are just synonyms, basically. But when you, go and do your exercise or you want to do some econometrics, you have to be, I think, explicit on what is the dependent variable and what would be the independent variable from the beginning. Okay. And so, for example, if you're interested in, the effects of hours of learning on your GPA, then GPA will be the dependent variable, and then the hours of learning that you dedicate in a week is going to be the independent variable. Okay. And so it's going to really depend on the research questions or the policy questions that you care about. But the idea is that we're trying to see the effect of X, which is the independent variable, on Y, which is the dependent variable. Okay. Any clarification on that concept before I continue? Okay, good.
I'm sorry, sir.
Yes, go ahead.
Just for confirmation about the dependent and the independent variable. So basically, the Y is the dependent variable that are affected by the dependent variable in the right side, and the dependent I'm sorry, the Y is the dependent variable that are affected by the right side of the independent variable, and the independent variable is basically a variable that are not affected by each other but only affect the dependent variables.
Okay, so
Thank
I'm
you.
going to start first. So the first one is Y. So yes, Y here in this context is the dependent variable. Okay. So usually we only have one dependent variable of interest. It could be the business performance, it could be the business profitability, it could be the student test score. Okay, so we only care about one dependent variable for the research question or the policy question that we're interested in. Okay, so in this particular chapter, we only care about one independent variable. Okay, and what we're trying to establish is that whether or not the independent variable has an effect on the dependent variable. Okay, so that's what we care about. Now, in practice, as we discussed just a bit last week, it could be that X and Y are actually correlated, but they're not necessarily a causal relationship. So in this particular case, then Y could affect X. But for this discussion, moving forward, we care about whether or not X affect Y, but not the other way around. Okay. Okay, so I see. Okay. All right. So I guess with that, concept clear, I'm gonna go and then discuss several features of this model. Okay. Now we know that Y and X, they are basically our variables. Okay. Now, it's very, very important to distinguish between variables and parameters, okay? Now, in this particular model, beta 0 and beta 1, these are called parameters of the model, okay? So in particular, beta 0 is called the intercept, and then beta 1 is called the slope, okay? Though beta 0 is also important in the model in general, but what we care about is actually beta 1. Okay. Again, beta 1 is the value of the parameter in the population. Okay. So this is a parameter in the population. Okay. We don't know what's the value of the parameter. It's something that is unknown. So if you guys remember and you guys recall the concepts in statistics course, we don't know what's the value of the parameter of the population in general. And so what we're trying to do is that we're going to get some sample, and then using that sample, we're going to try to estimate the value of beta 1 in the population. Okay, so I'm just going to write it that beta 1 is unknown. Okay. Now, sometimes we also use different Greek symbols when writing the regression model. Sometimes we use betas, sometimes we use alphas, as in this case. Sometimes we also use delta. Some people use gammas and stuff like that. But the most usual, like the most used term is going to be the betas. Now, alpha 0, alpha 1, beta 0, and beta 1 are basically the same. They're just representations of the model parameters, okay? So don't get confused if you see a textbook writing it using the alphas and other textbook writing it using the betas. They're just basically a representation of the model parameters, okay? Okay. Another feature of the population regression function is going to be the use, okay? Okay, so I'll continue. Sorry for the hassle. I think there are issues with the internet. So basically, the textbook define U as the error term or the disturbance. You know, we discussed this quite intensively last week. I personally don't like the term disturbance. And so what is U? Anyone wants to share their thoughts?
Can I try, sir?
Sure, go ahead. Yes, please.
Oh, yeah. As we discussed last week, the term U is the unobservable variables outside our current model that actually affects the dependent variable.
Okay, all right, that's very good. So basically, U is going to represent unobserved variables, unobserved characteristics, and these unobserved variables affect the dependent variable of interest. Okay, and you know, we don't include these variables into the regression specification for various reasons. Okay, so it could be the fact that we don't observe the variable, and so during the data collection process, the variable was not measured. It could be the fact that there's actually the variable, but for some reason we don't include it in the regression specification. We're going to talk about this more on the next meeting on chapter 3. Okay, but again, the idea is that the term U is something that we do not observe and we do not control in this model. So what do we mean by we do not control in this model? When we mean we do not control in this model, we don't put it as one of the independent variables in the model. Okay. Another key feature of this unobservable variable is that they also affects the dependent variable of interest. Okay, so the term U includes unobservable variables, something that we do not control in this model, and it also affects Y. Now, consider a model relating farming yield and fertilizer use. Okay, so I'm not going to go specific into the units, but the idea is that you have yield. Basically, this is the farming productivity on the left-hand side as the dependent variable, and you have fertilizer on the right-hand side. Basically, fertilizer is one of the inputs that farmers use to improve the productivity of the farming. Okay. Now suppose that yield is measured in kilogram per hectare and then fertilizer is measured in kilogram. Now I'm going to give you guys about 45 seconds to try to think about what are the unobservables in yield. Okay, starting from now. If you guys have any idea, please unmute yourself and then share your ideas with your classmates.
Sorry, sir. Maybe I can try, sir.
Sure, go ahead, Chopin.
Maybe weather, sir. Weather.
Okay, very good. Yes, weather, I think it's an important factor that determine, the productivity of the farming and particularly the yield. For some crops, it's not good if the weather is relatively wet. For some crops, it's not particularly good if it's too dry. So for example, I've been doing a lot of research on tobacco farming, and tobacco leaves are not doing pretty well when the weather is quite wet. Okay, so if it gets too rainy, particularly on the dry season, the quality of the tobacco leaf is going to be significantly lower. Okay, and thus if the quality is lower, then the price that the farmers get is going to be low. Okay, so I'm going to list weather as one of the important unobserved variables here. Can you guys think of other unobservable variable?
Certainly.
Oh, go ahead. Okay, Arzak, go ahead.
Is pest and disease included?
Okay, so it could be that there are pests and then diseases specific to the crops that these farmers planted. Very good. Other unobservable that you guys think are important in determining the yield?
Sir,
Okay, go ahead. You guys can raise hand and then I'm gonna go one by one. Okay, Zaki, go ahead.
I'm thinking farmer ability and motivation to do their farming.
Okay, very good. I think this is important in the sense that farmers have different ability. Farmers have, they have different knowledge on the use of fertilizer and farming in general. So I think that's a particularly good variable to include. Okay, Alexander and then David, go ahead.
Another variables that I can think of is probably the quality of the land, sir.
Okay, very good. I think that's also important. So farmers have different land quality. Sometimes they also have different positions in the terrain. So they could be on top of the terrain, they could be on the middle, and they could be on the bottom of the terrain. And then the types of crops that they can plant is quite different, and then the productivity is also quite different. So it's very interesting that the quality of land can actually determine your productivity. Okay, David, and then the last one will be Matthew. Go ahead.
Right. Maybe it may be affecting the yield, the technology used by the farmers. Like if it is more advanced, then the yield will be much more yieldful. Yeah.
Okay, very good, David. So I think technology is a very important feature. So different farmers have different technology adoption. And so some farmers are just quite good at adopting technology. Some farmers don't. And what's interesting is that not only that the technology is going to affect the yield, but at the same time, the technology could also determine the amount of fertilizer used. And so I think this technology variable is a very important variable that, if we can observe the technology, although it's quite difficult to measure one, we should have it in the model. Okay, last one, Matthew.
I was thinking maybe the frequency of irrigation or quality of the water, sir, and maybe the number of farmers that collects the crop.
Okay, very good. So I think irrigation is also another feature that we should care about. A lot of farmers, particularly in the dry season, they can't plant commodities that are requested by the market. The reason is that they don't have the proper irrigation access or irrigation system to allow them to plant specific commodities during the dry season. And so they're left with no choice to plant plants that are suitable for the dry season, and then the use of relatively smaller amount of water. So irrigation definitely is important. Another feature that is not observable in this model is going to be the size of the land, and then the size of the land is also going to determine the number of labor used for the farming. So this is very good in the sense that from small discussions, not only that you understand that there are many unobservable variables, but at the same time you understand that unobservable variables affect the dependent variable of interest, in this case is yield. And then at the same time, the unobservable is also correlated, could be correlated with fertilizer. In this case, for example, is the technology. Okay, so very good discussion. I'm gonna move forward into estimating the parameters. Okay, so again, I'm just gonna emphasize that we have the population. So the population has a characteristic, and the characteristic that we care about from a population is called parameter. Okay, now in this particular model, the parameters are beta 0 and beta 1. Okay, so this is the parameters that we care about. Now, what we want to do is that before I go there, beta 0 and beta 1 are something that we don't know. So this is unknown. And so what we want to do is that we want to recover beta 0 and beta 1 from the data. So the big question is, how can we recover beta 0 and beta 1 from the data? Okay, so this is going to be the discussion that we're going to have in several slides. Basically, we want to try to estimate the value of beta 0 and beta 1 using the data that we have. Okay. All right. But before I go there, I'm just going to set aside probably 5 minutes. And so, in the 5 minutes, what I want you guys to do is write, a specific question that you're interested in. And then for that specific question, determine the dependent variable and then the independent variable. Okay, and then write the model in a piece of paper on your computer, on your tablet, and then I'm gonna probably ask a couple of you to share what's the question and what are the variables that you list. Okay, so let's start now, and then in a minute or two, I'm going to start asking some of you guys to share about some of the questions that you care about. Okay, let's start. Okay, anyone wants to share? I'm gonna take two students first, and then we'll see where we can go from there. Okay, anyone wants to share? Please raise your hand, and then I'll Okay, we have Zaki. Matthew, are you interested? You still have your hands up?
Yes, sir.
Okay. So let's take Zaki and Matthew, and then probably I'm going to get one more. All right, let's start with Zaki first. Go ahead.
Okay, so my question of interest here is it concerns fighters who fight in an MMA match, and my question is whether the number of punches taken to the head create brain damage.
Okay, thank you, Zaki. So I think this has been the interest of sports. I think in the past 3-4 decades. So it's not only specific to MMA, but it's also true for boxing. It's also true for American football. If you guys follow American football, it's also true for rugby. It's also true for recently is football or soccer, as people in the United States said it. So it's very interesting question, and yes, there are I think studies that try to look the relationship between the number of clashes that a sportsman experienced during his career, and then the probability of experiencing a head trauma, particularly in later years of their life. So very interesting. Okay, Matthew.
Okay. My variable of interest would be poverty, sir. That's the dependent variable. And I'm interested in finding the relationship, whether or not higher usage of mobile payments and also accounts savings and borrowings ownership relates to poverty reduction. So whether or not countries that have higher rates of mobile payments and greater degree of financial inclusion have lower poverty. I guess that would be the research interest.
Okay, very interesting. So I guess the government, particularly the the National Committee on Financial Inclusion, have been trying to promote programs to improve financial literacy, financial inclusion, and then eventually hopefully a lot of those programs can have intersection with poverty reduction program, and at the end of the day, it's going to reduce poverty in Indonesia. So it's very interesting. So I'm going to hear a different perspective, and so I'm going to try to appoint a student. Nadia Utami, do you have an idea to share?
Yes. So for my example, I wrote about, the question is about the amount of sleep with productivity rate. And with that, the independent variable would be productivity rate. And, it's the other way around. The independent variable would be the sleep, and the dependent would be productivity rate.
Okay, thank you, Nadia. Yes, again, this is another important, I think, research question, and a lot of people actually care about this research question. They want to know whether or not there is a relationship between the amount of sleep that you clock in and the productivity that you produce in a given day. So it's very interesting, and I think it deserves a lot of attention. And if you talk about scarcity of the time, and one of the kind of like the inputs that people who cares about scarcity, and particularly on the effect of scarcity on productivity, one of their inputs was that try to get enough sleep. Okay, all right. So I'm hearing a lot of interesting feedbacks from from students. So I think we can now move on to try to estimate data 0 and data 1 from the data. Okay. So for example, if the left-hand side is productivity of individual I, okay, and then beta 0 plus beta 1, and then this is the amount of sleep that the individual get on average in the past week, for example. And of course, there are unobservable that we don't control in this model. Again, our interest is to try to estimate beta 0 and beta 1 from the data that we have. So this is basically our main interest. Okay, so the first question is, how do we recover beta 0 and beta 1 from the data. So before we do any estimation and before we do anything technical, what we need to do is we need to fulfill key assumptions in the model. Okay, we'll try to talk about the key assumptions, and then the second one, how do we actually recover beta 0 and beta 1 from the data technically? So among others, we're going to discuss what's called the ordinary least square estimator, or called the OLS estimator. Okay, and so these are going to be the big two discussions that we're going to have in the next few slides. Okay, so let's start first with the derivation of the OLS estimates. We're not going to really derive the OLS estimates, but if you are interested in the derivation of OLS estimates, we do have that in the appendix. So it's just going to take a bit of remembering of mathematics, particularly partial derivative, and a bit of algebra, and I think you'll be able to get the results. Okay, but if you want to do it, you can have it. You can try to look at it at the appendix. Okay, so let's answer the first question: how do we recover beta 0 and beta 1 from the data? So the answer is going to be on the assumptions. Now, there are several assumptions that we care about. However, in this particular discussion, we're just going to care and discuss about one key assumption. Okay, and the key assumption is going to be called the zero conditional mean assumption. So I cannot stress you enough the importance of zero conditional mean assumption. And this assumption is going to be, I guess, like the basic foundation of econometrics in general. Okay, and the issue that I've experienced in the past 5 years, for example, is that a lot of people put a lot of attentions on the variable. They put a lot of attentions on the distribution of the variable, but they don't really touch upon the main or the key assumption, which is the zero conditional mean assumption. And so this is very important for you guys to really understand the meaning behind the zero conditional mean assumption. Okay, so I'm just going to go back to the previous examples that were raised by the students. So we're interested in looking at the effect of sleep on productivity. Okay. Okay, so here the main or the key assumption is the zero conditional mean assumption. What does it say? It says that there is no correlation between the factors that we do not observe and the amount of sleep that we get. Okay, so that's basically like the general term. I'm not going to get into a specific, but for now, we're just going to try to assume that. Another example that we'll raise is that the number of punches that they've experienced during their MMA career and the probability of experiencing head trauma or like head trauma related diseases in the future. So the assumption here is that the factors that we do not observe is not correlated with the number of punches that they get. Okay, so this is going to be the key assumption. Now, what I think we need to highlight is that since the key assumption involves an unobservable variable, it cannot be tested statistically. Okay, and so you have to argue that this assumption is true, and from my experience, it's actually going to be quite difficult for you to kind of like argue that the assumption is true, but it's something that you guys need to do later on. Okay, now this is just a simple I think mathematical statistic. So if you guys remember, so the expectation of y is going to be beta 0 plus beta 1 x plus u, conditional on x. So this is going to be, since expectation is a linear operator, so we're going to have it as beta 0 conditional on x, and then expectation of beta 1 x conditional on x, and then expectation of U conditional on X. Okay, so remember beta 0 is a parameter, so it's a constant. Okay, so it doesn't vary with the value of X, and so basically this is just beta 0. Okay, and so what is the expected value of beta 1 multiplied by X conditional on X? Okay, so basically this is just beta 1 expectation of X conditional on X. Okay, beta 1 times expectation of X conditional on X is just beta 1 times X. Okay, so this is just beta 1 times X. Now my question for you is, what's this value here given the assumption? So given the assumption, the zero conditional mean assumption, this is going to be 0. Okay, so remember this assumption. Okay, and so what does it say? It says that the predicted Y, okay, is going to be, Y could be predicted just by X, okay, but not on the factors that we do not observe. So I guess that's the meaning of this particular line. Okay. Now I'm gonna give you guys a more concrete example, and so you guys will be able, to understand more about the idea of zero conditional mean assumption. And so suppose that we're interested in the wage equation. This is something that we touched upon last week. This is part of the Mincerian equation. So we care about the wage. That's the dependent variable on the left-hand side. And we care also about the independent of interest. In this case, is the years of schooling. Okay. So the zero conditional mean assumption implies that there is no correlation between the factors that we do not observe and then education. Okay, so we assume that there is no correlation. Now, this is a tip. So the first thing that you might want to do, okay, before we do some discussion, is that try to pick one unobservable variable that affects wage. Okay, now in this particular case, I'm just going to take ability. So ability could be knowledge, it could be their motivation, and stuff like that. Okay, so the question is whether ability correlates with education or not. If ability doesn't correlate with education, then your zero conditional mean assumption is fulfilled. Okay, but if ability is actually correlated with education, then the zero conditional mean assumption fails. Okay, all right. So before we go on and discuss whether or not ability is correlated or is actually uncorrelated with education, we'll see what the zero conditional mean assumption says. Okay, now the zero conditional mean assumption says that the average level of ability is the same regardless of years of schooling. Okay, so this implies that there is no correlation between ability. So what I mean by correlation is that individuals with higher ability are more likely to achieve higher years of schooling. Okay, and the zero conditional mean assumption says that whatever the ability or the average ability, it doesn't really matter on the years of schooling. Okay, so no, my question to you is, is the assumption sensible or not? What do you guys think? Do you think that there is a correlation between ability and the years of schooling, or there is no correlation between ability and years of schooling? Any thoughts? Yes,
I guess there is, sir, because some people drop out of school because they fail.
Yeah. So if we talked about on average, then yes, on average, there is a correlation between ability, innate ability, and the years of schooling. Okay, so in that case, then the assumption is actually false. Okay, so the zero conditional assumption doesn't hold in this particular case. Okay, so this is the way that you have to try to approach your model, is that, okay, I'm interested in the relationship between sleep and productivity. Okay, but at the same time, are there any unobservable variable that is correlated with the amount of sleep at the same time? Okay, it could be age, it could be marital status, it could be the number of children, it could be the number of jobs that they care about, and so all of this kind of like characteristics can be correlated with the amount of sleep. But again, don't forget that this unobservable variable actually affects the dependent variable of interest. Okay. All right. So I guess this is going to be very key for a lot of you to really understand the meaning behind zero conditional mean assumption. So please let me know if you have any clarification or questions. Okay. Okay, just to go back, just to make sure that everyone is on board with the idea. Again, the zero conditional mean assumption requires that there is no correlation between the factors that we do not observe and the main independent variable of interest. In this particular case is education. Okay. Now, to verify whether or not the assumption is true or false, what you can do is just identify a particular variable here. So, for example, an unobserved variable that is important in a wage determination is ability. Okay, so you should ask yourself whether or not there is a correlation between education. Okay, so if you think that more able people obtain higher years of schooling, then the assumption fails, or the assumption is false. Okay, and so again, moving forward, I think understanding zero conditional mean is going to be very important for you, particularly if you guys are interested in causal relationship. Okay, but again, in reality, we're going to find that a lot of these cases and a lot of these models, the zero conditional mean assumption, are not going to be verified. But doesn't mean that you cannot stop learning. But I think it's just good to understand that, okay, there are limitations, and you'll be able to understand what's the limitations of the model, given that the zero conditional mean assumption doesn't hold. Okay, so instead of just not doing any econometrics at all, but still do econometrics and see and understand the caveats and the shortcomings of each model. Okay. Now, given that the only variable that should predict y is going to be x, then this is just a graphical depiction on the conditional value of y on x. Okay. So the conditional value of y conditional on x is going to be a linear function of x. So for any given value of x, so for example, for x equals to x1, then the distribution of y is going to be centered about the expected value of y given x. So which one is the expected value of y given x? So the hard line here, this is the expected value of y conditional on x. And the distribution of y is going to be centered around the predicted value of y conditional on x. Okay. So this is going to be a depiction, a graphical depiction, if we fulfill the zero conditional mean assumption. Okay. So now let's get into the technical detail. Again, we write the basic model, and the basic model is the population regression function. Okay, so we're gonna in this particular slide differentiate between parameters as well as statistic. Okay, now we know that beta 0 is the intercept. We know that beta 1 is going to be the coefficient of x, which is also referred to as the slope, and we care most about this beta 1. Okay. Now, the estimated betas are going to be denoted as beta 0 and beta 1. Again, beta 0 and beta 1, this is something that we observe in for the population. Again, we don't know what the value is, And then when we have the sample, we're going to use the sample to estimate beta 0 hat and then beta 1 hat. Okay, so if you go into the textbook and then you see that there are equations with beta 0, beta 1, but there are also equations with beta 0 hat and beta 1 hat, then you'll be able to understand what it means by beta 0 hat and beta 1 hat. Okay. All right. So if you have beta 0 hat and if you have beta 1 hat and you multiply beta 1 hat with the actual value of x, then what you'll get is predicted y. Okay, so the predicted y is going to be denoted as y hat. Okay, some people call it the fitted value, some people call it the predicted value of y. Both are interchangeably used. Okay, all right. So basically, you have y, which is what you observe in the data, and then you have y hat, which is what you predict from the model. Now, the difference is going to be called residual. Okay, so this is going to be referred to as the residual. Now, residual by no means is equal to the unobservable variable. Okay, so it's two different concepts. Okay, so U is unobservable variable in the population. Residual is kind of like the artifact of the model that we care about. Okay, all right. So before I go on, any clarifications on the notations that I use in this slide? Okay, so please distinguish between beta 0 and beta hat, and then please also distinguish between beta 1 and beta 1 hat, because they're these two are very different concepts. Okay. All right, so I guess I can continue. So the big question is how, to estimate the model. So basically, we need a data to estimate the model. Okay. Now, one of the key, another key assumption that we need is that we need a random sample from the population. Okay. So you have the population, and then it's very costly for you guys to get the population values and stuff like that. And so what you do is that you get a sample. Okay. So what is the key criteria such that we have a representative sample? So the key criteria such that we get a representative sample is that we randomly select sample from the population. Okay, so if we do so, we're going to get what's called a representative sample. If we do not get randomly selected sample from the population, then we're going to get what's called a bias sample. Okay, so if you get a bias sample, then your estimate or your estimates are going to be biased as well. Okay, so for this simple linear regression model, what you're going to get is a pair of y and x for each entity. Okay, and so from the first entity, you'll see what's the value of x and the value of y from the second observation or the second entity, and so on until you have all the entities that you care about. So for example, if your entity is an individual, you want to collect the productivity, which is y. Productivity could be reflected as wages, for example, and then x is going to be hours of sleep. Okay. In another example that you raise, y is poverty rate, and then x is the share of individuals with access to financial services. And so these are going to be the idea. Okay. All right. So since we have established the idea of recovering the data, so to recover the parameter beta 0 and beta 1 from the data, we need the key assumption, which is the zero conditional mean assumption. We also need the we also need the data to be able to estimate it. Okay. Now, given that we already have the data, given that we already fulfilled the zero conditional mean assumption, now what we're going to do is that we're going to estimate the model. Okay. So when I mean estimate the model, again, what you care about is beta 0 and beta 1. We don't know the value of beta 0 and beta 1 because it's a parameter value. And so what we're going to do is that we're going to use the data to try to estimate beta 0 hat and then beta 1 hat. Okay. And so when we say that we estimate the model, we actually estimate beta 0 and we estimate beta 1. And the estimated beta 0 is called the beta 0 hat. And then the estimated beta 1 is going to be called the beta 1 hat. Okay. And so what we're going to do is that we're going to choose beta 0 and beta 1 such that it minimizes the squared residual. Okay. Remember, this is yi, and this is going to be the predicted or the fitted value. Okay. And you guys remember that the difference between the actual value and the fitted value is going to be the residual. Okay. And so we're going to choose beta 0 hat and beta 1 hat such that the squared residual, the sum of the squared residual, is the minimum. So it doesn't have to be 0, but we want to choose beta 0 hat and beta 1 hat such that the sum of the squared residual is minimum. Okay. So this is a calculus optimization approach, and you can review the materials in your math for econ 2 sequence. Okay. We're going to leave this for your second problem set. Okay. So I'm just going to give you an idea before I open up, a chance for students to ask. So basically, this dot here is the actual pair of y and x. This is something that we observed in the data. Okay. Now, again, once you get the data and then try to estimate it, you'll get what's called the regression line. Okay. Now, for each dot here, so for example, this is the true value of y. Okay. And this is what's called the predicted value of y given x. Okay. So the difference is going to be the residual. Okay. So suppose that we have from these 4 observations, okay, 4 residuals. Actually, this is hats. Just want to make sure that you guys get it. And these are the residual. And so what we're going to do is that we're going to square the residual, and then we're going to sum it. And then what we're going to do is that we're going to try to find beta 0 hat and then beta 1 hat such that it minimizes the sum of the squared residuals. That's the idea of regression. Now, when you take time to actually do the optimization, if you spend time and then do the optimization, then you'll get what's called the OLS estimators. Okay, so the estimators are for both the beta 0 hat and then for the beta 1 hat. Okay, now I know that we only focus on beta 1 hat, and so let's just focus our attention to this one. Okay, so we have a ratio of, this is called the covariance between x and y. There's a sample covariance of x and y. And then in the denominator, anyone remembers what this is? Anyone recall what this is?
Standard errors.
So it's not standard error. We're going to get into standard error, but you're getting it there. It's actually the variance of x. Okay. So basically, beta 1 hat is the ratio between the covariance between x and y and the variance of x. Okay. So I'm going to go into the next slide. So I'm just going to write it as the following. So beta 1 hat is going to be the sample covariance between x and y, and also the sample variance of x. Okay. What's the value of variance? Can it be negative? Can variance be negative? No. Okay. So variance is always positive. Okay. So the value of beta 1 hat, whether beta 1 hat is positive or is negative, it's going to be dependent on the sample covariance. Okay. So if the sample covariance is positive, then beta 1 hat is positive. Okay. However, if the sample covariance is negative, then the value of beta 1 hat is going to be negative. Okay. And so the correlation between X and Y is going to determine the slope of beta 1 hat, or the value of beta 1 hat. Okay. All right. So any questions before I move on to the next slide? Go ahead. Okay.
Excuse me, sir.
Yes, go ahead.
May I ask a question?
Yes, please.
So I was wondering, because you previously mentioned that the OLS intended to minimize the sum of squared residuals. Why don't we try to find instead the minimizing the residuals itself, the absolute residuals? So that's my question.
Okay.
Thank you, sir.
So very good question. So basically, it's not the only method that is available out there. There are other methods that we can use to try to estimate beta 0 and beta 1 hat. One of the reasons why we choose OLS estimation is that later on we'll see that OLS estimation is, given the key assumptions, it's the most efficient. It's an unbiased and the most efficient estimator that we can think about. Now, in terms of why do we choose beta 0 hat and beta 1 hat such that we minimize the sum square of the residuals, is that just going back to this graph. And so what we're trying to do is that we're trying to have, we're going to have a line, which is the black line here, the solid black line, such that we minimize the sum square of residual. Okay, so if we don't use that as a criteria, to estimate beta 0 and beta 1 hat, it could be the fact that it could be the fact that the lines are like this. Okay, or the line is like this. Okay, and so we choose to minimize the sum squared of residuals so that we have a criteria such that a particular line fits. Okay, so that's kind of the idea. Okay, hopefully that gives you some answer to the questions. I think given the time, I'm just gonna continue first. Okay, so I'm gonna go back to this slide. Okay, so again, we have the dependent variable of interest, which is the salary variable. We also have the independent variable of interest, which is the return to equity, or the ROE. If you guys care about financial management, I think these are some of the measures that you guys have encountered in the past. Okay, so given the estimated beta 0 hat and then beta 1 hat, we have what's called the salary hat. So the salary hat here is basically the fitted value or the predicted value. Okay, and now the difference between salary and the salary hat is going to be U hat. Okay, and U hat is called the residual. Okay. Now, let's give you another example. Actually, this is a follow-up from the previous slide. So let Y be the annual salary in terms of thousands of dollars, and then X be the average ROE in percentage for the CEO's firm. Again, the basic model is salary equals to beta 0 plus beta 1 ROE plus some unobservable. Okay, and the OLS estimates are, beta 0 hat is 963, and then beta 1 hat is 18.501. Okay, so again, I just want to remind you that 963 is beta 0 hat. It's not beta 0, it's not the value in the parameter, it's actually the estimated value, okay, which is the beta 0 hat. 18.501 is beta 1 hat, which is the estimated beta 1. Okay, now let's do the interpretation for beta 0 first. Okay, now what do we mean by the beta 0 hat, which is here? Okay, so suppose that ROE is equal to 0. Okay, so if ROE is equal to 0, then this is 0. Okay, so it means that on average, the average salary for firms with 0 ROE is going to be $963,000. Okay, why is it $1,000? Recall that the unit for Y is $1,000. Okay, now that's going to be the interpretation of the beta 0. Okay, so the beta 0 is going to be the value or the average value of the salary or the dependent variable, given that the value of X, which in this case is ROE, is equal to 0. Okay, now at the end of the day, we don't really care that much on the beta 0, but we definitely care about beta 1 hat. Okay, and so we want to try to learn how to interpret the coefficient. Okay, now suppose that the 0 conditional mean is satisfied. Okay, now if the other factors in U are held fixed, so that the change in U is 0 or delta U is equal to 0, then X has a linear effect on Y. Okay, and so the change in Y is just going to be beta 1 times the change in X. Okay, that is if the change in U is 0. What does it mean? It means that we make what's called the ceteris paribus, which is, this is the effect of a change in X on Y, ceteris paribus, okay, which is that every other factors are held constant, okay? And so the only change that occurs is a change in X, and then that change in X is going to affect the value of Y, assuming that all the other variables are held constant. And so if you think about it, this is like an experiment, right? You change the value of X, and then conditional on the value of beta 1, you'll be able to get, or you'll be able to predict the change in Y. This is a very powerful result. Okay, you're trying to change the value of one particular variable, which is X, and then see the effect on Y, which is quite interesting. Now, again, if you're interested in applied economics, then I think this is going to be the key, one of the key features. Okay, and so let's start and try to discuss the meaning of 18.501. Okay, now assume, so this is a very big assumption, assume that the 0 conditional mean assumption is satisfied, then the interpretation is as follows. If the return on equity increases by 1 percentage point, then the salary will increase by 1 percentage point multiplied by 18.501, which is about $18,501. Okay, so again, for every increase in return on equity by 1 percentage point, the salary will increase by about $18,501. Okay. All right, so that's going to be the interpretation of the variable. Any questions from this? Okay, so you saw the interpretation of Vera 0. Now you also see the interpretation of Vera 1 hat. Okay, so hopefully you'll get an idea on the way to interpret it. Okay, any clarification?
Sir, I want to ask
Yeah.
for the number 963 and 18.5, is it actually usually given, or do we need to calculate them? And how do we calculate them if the data entries are so many of them, sir?
Yeah, so that's basically something that we're going to learn later today. I'm going to provide you with an illustration of doing a simple linear regression in Stata. Okay, so again, 963 is going to be the estimated beta 0, and 18.501 is going to be the estimated beta 1. Okay, so you basically have to estimate these values from the data. Okay, we're gonna show you how we go about that in Stata. Okay, any questions before I go and discuss the goodness of it? Okay, good. And so there are some important quantities that we're interested in. Okay, so there are some important quantities that we care about. So the first one is going to be the total sum of squares. Okay, so this is the variation. Okay, this is the variation of the dependent variable, which is the variation of y. Okay, and so the variation of y, SST, can be decomposed into two parts. Okay, so the first part is the variation of the variable that can be explained by the data. Okay, so again, the first part is going to be the variation of the model, the variation of the data that can be explained by the variation of the model. Okay, the second one is going to be the residual sum of squares, which is the variation of the data that cannot be explained by the variation of the model. Okay, so this is the decomposition of the total sum of squares that we have in the data. Okay, so basically, it's a variation that can be explained by the variation of the model, and then there are variations that cannot be explained by the variation of the model. Of course, if we care about prediction, okay, if we care about prediction, then we care that SSE explain a lot of the variation in the data. Okay, and so for that specific reason, we want an indicator, which is a measure of goodness of fit, and we call it the R square. Okay, so R square is going to be the ratio between the variation of the model that can be explained by the variation of the data, the variation of the data that can be explained by the variation of the model divided by the total variation of the data. Okay, so R square measures the predictive, again, I'm just gonna highlight this. It measures the predictive power of the model. And the value of R square is always going to be between 0 and 1. If the value is close to 0, it means that your variable is actually not that good at predicting y. But if your value is near 1, then your variable x is actually a perfect predictor of y. Okay. Now, some of you guys are, going to have a career as a financial, someone who does financial modeling. R square is going to be one of that important indicators that we care about. Okay. Now, another thing that is important to note is that R squared doesn't really depend on the units of measurement. In other words, it's measurement free. Okay. Okay. So, for example, suppose that when we do a regression on the salary and the return on equity, we get that the R square is 0.0312. Okay. So how do we interpret this? So the book provides you with a reference, and so you can always revisit it in the book. But it says that about 1.32% of the variation of the data can be explained by the variation of the data. Okay. Another example is the R-square from the wage and education regression. Okay. So it means that about 16.3% variation of the data can be explained by the variation of the model. Okay. For the other words, the variation of the model can explain 16.3% of the variation of the data. Okay. Now, I just want to point out to you that a high R-square does not necessarily mean that the regression has a causal interpretation. Okay. So again, R-squared doesn't have anything to do with causal interpretation. Okay. So it is actually a good measure. It's actually a good indicator for prediction. It's good for perhaps doing forecasting, but it's not. It doesn't have anything to do with causal interpretation. Okay. It doesn't mean that if you have a high R-square, then you've uncovered a causal interpretation. It doesn't work like that. It also doesn't mean that if you have a low R-square, it doesn't mean that you cannot identify a causal relationship. Okay. So again, what it means is that the value of R-squared doesn't have anything to do with causal interpretation. Okay. So I guess I'm going to stop here first, and then we're going to take a break. And then after the break, I'm going to provide you with some discussion on the functional forms, unbiasedness of OLS, variation of OLS estimators, and then I'm going to provide you an example in Stata. Okay. But before we take a break, any questions?
Sir, I have one.
Yes, go ahead, Zaki.
With regard to the goodness of fit, I would like to know whether if we find that there is a goodness of fit between two variables, and since you mentioned something about financial modeling, let's say if we find a goodness of fit between revenue and say capital expenditure, does that mean that we can forecast revenue using the amount of capital expenditure of the company, just for the sake of example?
Yeah, exactly. So for the sake of example, yes, you'll be able to use, capital expenditure as a predictor of revenue. It may not be the only predictor of revenue, but it's actually a good predictor of revenue. And then another point that you can make is that although capital expenditure is a good predictor of revenue, it doesn't mean that capital expenditure has a causal effect on revenue. Okay. Again, predictor doesn't mean causal relationship. I guess that's the point that I like to make. So yes, you can do forecasting, you can do prediction using variables that you think are important, but it's going to be quite difficult to claim causal relationship. It's a good predictor, it's good for forecasting, but doesn't mean that it's good for causal relationship.
Okay, thank you, sir.
Sure. Any other? One more, perhaps? Okay, so if not, let's take a break and then be back by 3 p.m. and then I'm going to provide you with an illustration of how to do data analysis using Stata. Okay. So yes, so that's basically an illustration, in Stata. So we have the two variables of interest. We have the salary, and then we also have the return to equity. And then we're going to estimate it using Stata. It's very straightforward. It's very intuitive. And so I don't think that we should focus on the estimation side, the technical side of the estimation. And so what I think it's important is for you guys to be able to learn the key assumptions of the OLS regression. I think that's going to be more beneficial to your learning than the technical side of the estimation. But if you want to learn about the technical side of the estimation, I welcome you to do it. I think it's also very good to actually know the inside of the inside of the discussion. So, but that I think it's going to be quite useful for you. Okay. All right. Any question on Stata before I continue to the lecture?
Sorry, sir.
Yes, go ahead.
About the Stata. So basically, from our first meeting until the end of the meeting, we will use Stata, sir. Only Stata, not R and etc.
Yeah, for the purpose of the course, I'm going to show you in Stata. But if you want to use R, that's also fine. You can use R and then still upload Stata data. So I think it's going to be intuitive as well. And there are also resources that you can access, for Stata. So for R. So I don't think that's going to be particularly a problem for you. So yes, feel free if you want to use other software other than Stata. But for class purposes, I'm going to use Stata.
Thank you, sir.
Okay. All right. Good. So let me. Okay. All right. So let's go back to the discussion. We're gonna discuss about functional forms. So I think understanding functional forms are also going to be important. For the modeling side of this chapter. Okay, so let's start. So far the population regression line was assumed to be linear. So the expected value of y conditional of x is going to be a linear function, not only on the parameter, but also on x. Now this assumption is very strong. Okay, in many cases, there are reasons to believe that the relationship between x and y is actually nonlinear. Okay, so in applied work, you will often encounter regression equations where the dependent variable appears in logarithmic form. Okay, so for example, in earlier modeling, we have beta 0 plus beta 1x plus the unobservable variable. In some cases, we're going to do transformation of either the y or x, or actually both y and x. And one of the transformation that we usually use is the logarithmic transformation. Okay, so basically a logarithmic transformation is just the log of y equals to beta 0 plus beta 1x plus u. It's not the only transformation that's possible, given that we can also transform x into log of x. But this is just a preliminary introduction on how we can use the logarithmic transformation on y or the variable that we have in the model. Okay, so suppose instead that the percentage increase in wage is the same given one more year of education. So a model that gives approximately a constant percentage effect is the following. So we have the logarithmic transformation of wage on the left-hand side, and we have education on the right-hand side. Okay, so the log here indicates the natural logarithm or the ln. Okay, so in particular, if the change in the unobservable is 0, okay, so we fulfill the zero conditional mean assumption and stuff like that, then the interpretation is going to be quite different. Okay, so the interpretation is that for additional year of education, then the change in the wage is going to be beta 1 multiplied by 100%. Okay, so again, for each additional year of schooling, then the change in wage is going to be beta 1 multiplied by 100%. Okay, so it's going to be clear later in the later slide when I give you the example. So suppose that again we have the log transform wage on the left hand side, and we have education on the right-hand side. Okay, so how do we interpret this particular estimated coefficient? Okay, so again, for the interpretation, we have to multiply this by 100%. Okay, so for additional year of schooling, then wages is going to increase by 8.3%. Okay, so this 8.3% is what we economists call as the return to another year of education, or simply put, this is the return to education or the return to schooling. Okay, so for example, you do your investment, so you put in some amount of money now in a stock market, and then at the end of the year, you get a return of 20%. So it's a similar concept. So you invest additional year of schooling, and then say in 10 years in the labor market, you get, for every years of schooling, you get a return of 8.3%. So this is kind of like the story in the human capital investment theory. Okay. Another transformation is when you transform both y and x. Okay, so you have log y and then you have log x. Okay, now the interpretation is quite different. Okay, in the sense that we're going to have so beta 1 is going to represent a constant elasticity. Okay, so a 1% increase in x leads to a beta 1% increase in y. Now, suppose that beta 1 is 0.312. It means that for every 1% increase in x, okay, it leads to a 0.312% increase in y. Okay. Now, I just want to be very specific here that there are two different interpretations. Okay, depending on the data and depending on the units of the data. So one, you have the percentage change. Okay, so suppose that it's a 10% change or it's a 20% change. Okay, another interpretation, which I may not show it in this particular slide, is percentage point. Okay, so these are two very different concepts. So it's very good for you guys to be able or to start distinguishing between a percentage change and percentage points. Okay, so these two are very different. Now for this particular slide, this is called the percentage change. Okay, so for every 1% increase in x, it leads to a beta 1% increase in y. Okay, so when I get to example, I'm going to highlight an example of percentage point. Okay, all right. One more. So in the initial one, we have what's called the log-lin model, where we transform the y variable, and then in the second example, we have the double log or the log-log model, where we transform both x and y. Now, for the third model, we have what's called the linear log. So in this case, we transform, we log transform the x variable. Okay, so now the interpretation is the following. So a 1% increase in x leads to beta 1 times 0.01 units increase in y. So suppose that beta 1 is 27, then a 1% increase in x leads to a 0.27 units increase in y. Okay, so that's going to be the interpretation of the linear log. Now, note that the beta 0 represent the expected value of y given x equals to 1, because log of 1 is 0. Okay. All right. Any questions on the lin log model, the double log model, and the lin log model? Okay. Okay, so again, we can have flexibility in terms of specifying the model. And it's gonna actually help us to deal with several variables later on. So if you see some of the data from the Jeffrey Wooldridge data repository, you'll find that not only it provides you with the level variable, but it also provides you with the log transform variable, okay? And so you can use the log transform variable for estimation purposes. I'm going to also show you when I get back to Stata a way to actually create a log transform variable in Stata, which is very straightforward, okay? Now, so let's go to this slide and then discuss why we want to do linear regression. So we want to do linear regression because it's very easy. Nowadays, it's computationally simple or fast. So back in, say, 1987, 1990, you have to use, or a lot of people still use calculator to do OLS regression, okay? So it's going to take you a long, long time depending on the number of variables and also depending on the number of observations, okay? So doing a simple linear regression with just 2 variables, but say 100 observations can take you probably a day and a night to calculate the estimated coefficients of beta 0 and beta 1 back in the 1980s or the 1990s. But nowadays, it's just blazing fast. With all the computers that you have, PC or Mac, the estimation of a simple regression model is just, less than a second, very, very fast, okay? The speed is also not sensitive to the dimension of X, so you can have a very large variable and then the estimation is still going to be very quick. Excuse me. It's also relatively easy to interpret. It's recognizable, it's cross-disciplinary. So if you talk with someone from other disciplines, the likelihood that they understand OLS is also very high. It's somewhat flexible in terms of the way that we define the model, and it's also standardized, okay? All right, so what are the disadvantages of simple linear regression? So there are some disadvantages. So the first one is that it doesn't allow one to discover, nonlinear structure in the data, okay? So for this example, it's quite straightforward, okay? So it has a positive relationship, okay? But for this one, as you can see, there is a non-relationship between X and Y. However, we force the line to be a linear line, okay? So that's one disadvantage, and one that we're going to relax in chapter 3 when we talked about multiple linear regression. Another disadvantage is that suppose that we have an outlier or an observation, that is not quite common here. Okay, so this is also going to be a shortcoming of simple linear regression. Gosh, I'm sorry. Okay. My bad for the noise. Okay. And then the fourth problem is that there is an issue if the value of X doesn't really vary. So recall that the estimated value of beta 1 is going to be a ratio between the sample covariance of Y and X and then the variation of X. Now, consider this particular example. So in this particular example, the value of X doesn't really vary. So what happens is that the variance of X is going to be very low. So if the variance of X is very low, then what happens? What happens if you divide something with something that is very small? Then the value of beta 1 is going to get really huge, okay? So there are issues in simple linear regression, and what we're trying to do is that we're going to try to relax some of the assumptions, some of the modeling side of OLS next week in the chapter 3. And so some of the modeling that we're going to do is going to try to capture some of the nonlinear structure in the data, okay? But for now, we'll take it as it is. All right, So the next discussion is on the unbiasedness of OLS. So to talk about the unbiasedness of OLS, we have to talk about all the other assumptions, of the OLS. So again, the key assumption is going to be the zero conditional mean. However, there are also some assumptions that we care about. So the first assumption is going to be the model is linear in parameters. Okay, so you can have beta 0 and beta 1, they're both linear. Okay, so you cannot have, say, for example, y beta 0 square plus beta 1 to the power of 3 x plus u. Okay, so this won't happen. Okay, so what you need is that you need a model which is linear in parameter, which is beta 0 and beta 1. Okay, the second assumption is random sample. Okay, so again, you want to have a representative sample of the population. So to get a representative sample of the population, you have to do a random sample. Okay, you cannot do a purposive sample, you cannot do a convenient sampling, you need to do a random sampling of the data of the population. Okay, and then assumption 3 is that the sample variation in explanatory variable. Okay, so basically the values of explanatory variables are not all the same. Okay, now going back to this particular example, this is a case where the value of x doesn't really vary, and if the value of x doesn't really vary, then we're going to get an issue in the estimation. In the estimation of beta 1 hat. Okay. So the fourth assumption is the zero conditional mean assumption. This is something that we discuss a lot in the beginning of the lecture. And then assumption 5. So assumption 5, it doesn't have to do with the unbiasedness of the OLS, but I'm just gonna, mention it here for the sake of completeness. So assumption 5 is called homoscedasticity. Okay. So what does homoscedasticity mean? Homoscedasticity means that the variance of the unobservable variable conditional on x is going to be constant. Okay. Again, the conditional variance of the unobservable is going to be a constant. Okay. So that's why it's called homoscedasticity. What happens if it's not constant? Then it's going to be called heteroscedasticity. Okay, so we're gonna discuss about homoscedasticity and heteroscedasticity in a specific chapter, chapter 8. But for now, let's take it as it is. Okay, so recall that there are 5 OLS assumptions. So we have linear in parameter, random sample, variation in x, zero conditional mean. And so under the assumption 1 to 4, then the expected value of beta 0 hat is going to be equal to the value of beta 0 in the parameter. Okay, and the expected value of beta 1 hat is going to be equal to the value of beta 1 in the parameter. Okay, so in other words, beta 0 hat is an unbiased estimator for beta 0, and beta 1 hat is an unbiased estimator for beta 1. Okay, so that's the idea of unbiasedness. Now, let's talk more about the idea and the interpretation of unbiasedness. The estimated coefficients may be smaller or larger depending on the sample that is the result of the random draw. Okay, so I'm going to give you guys an example. Suppose that we have a value in the parameter which is beta 1. Again, we don't know the value of beta 1, but suppose that we do. Okay, suppose that the value of beta 1 in the population is 10. Okay, now again, you cannot get the observation of the population, so what do? You take a random sample. Okay, so suppose that you get a random sample, and then from the random sample your estimated is 10.2. okay, now you do another random sampling, and then from the random sample that you get, the second random sample that you get, you do another estimation, and then you get beta 1 hat of 9.6. Okay, so what does it mean? It means that the value of beta 1 hat is conditional on the random sample. If you have a different random sample, then the value of beta 1 hat is going to be different. Okay. But what we care about is not whether or not it's the same or it's actually different, but what we care about, if we do multiple random sample, then the expected value of the beta 1 hat is going to be very close to the true value of the parameter in the population, which in this case is equal to 10. Okay, so again, on average, they will be equal to the values that characterize the true relationship between Y and X in the population. Now, the question is, can we do multiple random sampling? The answer is no. What you do is that you basically just take one random sample, and then from that random sample, you get an estimate of beta 1 hat. And that beta 1 hat is going to provide you with measure or like an indicator of the true value of the parameter. Okay. So again, unbiasedness is a feature of it's a very important feature in mathematical statistics, and so hopefully you guys be able to get an idea of unbiasedness. Again, getting a value that is different to the true value in the population doesn't mean that it's biased. So unbiasedness is a value when we do repeated sampling. Okay. All right. Again, some comments. Just remember that unbiasedness is a feature of the sampling distribution of beta 1 and beta 0. If you guys, revisit your statistics 2 course, then you get an idea of what's called sampling distribution is. Okay. So unbiasedness generally fails if any of the 4 assumptions fail. Okay. So if you do not have a random sample, which violates the second OLS assumption, then you'll get a bias estimate. If you fail the 0 conditional mean assumption, you get a bias estimate. Okay. If you have a parameter that is not linear in the model, then your estimate will be biased as well. Okay. So that's going to be some comments about OLS estimator. Any questions? Go ahead. Any clarification? All good? All right, alrighty. And so far we discussed a lot about the estimation and the unbiasedness of the beta 1 hat. Okay, so recall that we have beta 0 and then we have beta 1 from the population, and then given a random sample of data and some assumptions, we were able to estimate beta 0 hat and then beta 1 hat. And if we fulfill the assumptions, including the key assumptions, then we're going to be sure that beta 0 hat and beta 1 hat are unbiased estimates of beta 0 and beta 1. So if you have an unbiased estimate, it means that it's good. Okay. Now, when we do estimation, not only that we care about beta 0 hat and beta 1 hat, but we also care about the variance of the estimators. Okay. And so we care about the variance of beta 0 hat, and we also care about the variation of beta 1 hat. Okay. And so the next discussion focuses on the variance of beta 0 hat and beta 1 hat. Why do we care about this? Well, at the end of the day, we're going to do some hypothesis testing. Okay. And so for the hypothesis testing, not only that we have to know the estimated coefficient beta 0 hat and beta 1 hat, but we also need to know the variance of beta 0 hat and beta 1 hat. Okay. So that's the idea on why we need variance of OLS estimators. Okay. Just to re-emphasize, in addition to knowing the sampling distribution of beta-1 hat is centered about beta-1, which means that beta-1 hat is unbiased, it's also important to know how far we can expect beta-1 hat to be away from beta-1 on average, okay? So this allows us to choose the best estimator among all, or at least a broad class of unbiased estimators. Estimator that has the smallest variance is called efficient estimator, okay? So the good thing is that OLS is actually an efficient estimator, okay? It has the smallest variance of all estimator in its class, okay? Now, the estimation will be much simpler under the fifth assumption, something that we discussed about several slides back, and it's called the homoscedasticity assumption. It means that the conditional variance of the unobservable is constant for all values of x, okay? So again, the homoscedasticity assumption says that the conditional variance of the unobservable is going to be constant for all values of x. Okay. Now, this is an illustration of homoscedasticity, okay? So for every x, or for all x, then the variance of the unobservable, so this is the variance of the unobservable, has a constant variance. What does it mean to have a constant variance? It means that the width of the distribution is similar for all x. Okay, so that's a graphical and a depiction of the homoscedasticity. Suppose that this is of x and this is expected value of y conditional of x. So suppose that for one x1 and this is for x2. Suppose that for this x1 the distribution is very narrow, but then for the other value of x, the distribution is very large. So this is a graphical illustration on the violation of the homoscedasticity assumption. In this particular case, we have what's called the heteroscedasticity assumption. Okay, but for the sake of discussion, we're going to assume that we fulfill the homoscedasticity assumption, and then later on, we're going to discuss what we should do in the case where we have heteroscedasticity. Okay. All right. Again, this is a simple illustration of heteroscedasticity. Mind you, this is going to be kind of like the reality. This is what we're actually going to face in the data set. And so even though that we assume homoscedasticity in this particular lecture, in this particular chapter, moving forward, we're going to acknowledge that there is actually heteroscedasticity, and it's actually a usual feature or a common feature in a lot of data set. Okay. All right. And so we discussed whether the predictive power of the regression line, which is the conditional y on x, differs across x. Okay. So if the predictive power of the regression line is similar, we have homoscedasticity. If the predictive power of the regression line is different across x, we have heteroscedasticity. Okay. Now, again, the predictive power can be depicted by the conditional variance of the unobservable, okay, which is the variance of the unobservable conditional on x. Okay. So if the conditional variance is constant, predictive power is also constant, but when the variance of the conditional variance of u is not constant, then the predictive power is also not constant. Okay, so basically, when the variance of unobservable is constant, we say that the error term exhibit homoscedasticity, or the error term is homoscedastic. Okay. All right. Any questions up to this point? I've introduced you quite a lot in this sub-discussion about homoscedasticity. So let me know if you have any clarification. So it may not make sense. It may be quite difficult to comprehend at the first contact or the first time, reviewing homoscedasticity, don't worry. It also took me some time to actually, get the idea of homoscedasticity. So just be patient. Keep reading, keep discussing, and then you'll get there in terms of understanding what homoscedasticity is. Okay. All right. So let's talk about the variance of the OLS estimators. Okay. So I guess there are two things. The first one is the variance. Okay. So sigma squared is going to be the conditional variance of the unobservable. Okay. Since we assume that we have homoscedasticity, then it's constant. Okay. The other one is just going to be the total variation of x, or the variance of x. Okay. Now the standard deviation of beta 1 hat, okay, is just a square root of the variance of beta 1 hat. Okay, this is straightforward, so I don't think we should discuss it more. Okay, so the sampling variability of the estimated regression coefficient will be higher the larger the variability of the unobserved factor. So if the variance, okay, so if sigma square is high, then the sampling variability is also going to be high. If the variance is low, then the sampling variability of the estimated regression coefficient will be low. Which one is more preferable? Higher sampling variability or lower sampling variability? When you do your estimation, which one is more preferable? High sampling variability or lower sampling variability? So it's actually ideal to get a lower sampling variability. Why? Because with the lower sampling variability, then you're more confident in the value of your estimate. Okay, so that's the idea. But if the sampling variability is large, then we're not going to be that confident with the estimated coefficient that we get. Okay. All right. So the next issue that we need to talk about is that we don't know the value of the variance. Okay. Again, this is a feature of the population. So sigma square is actually a parameter, and then the value is actually unknown. Okay. So if we don't know the value of beta, if we don't know the value of beta 0 and we don't know the value of beta 1, then we're going to get a data and then use the data to estimate beta 0 hat and then beta 1 hat. Okay. Now, similarly, if we don't know the value of sigma square, then what we're going to do is that we're going to use the data and then we're going to estimate sigma square. Okay. So again, this is the value in the population. And so we're going to use the data, and then using the data, we're going to estimate sigma hat square. Okay. So sigma hat square is basically the sample variance of the residuals. Okay. Again, sigma square is going to be the variance of the unobservable. Sigma hat square is the sample variance of the residuals. Please distinguish between population regression function and the parameters, and sample regression functions, and then statistic. Okay. Now, why do we need the fifth assumption? Okay, why do we need the fifth assumption? Because with assumption 1, 2, 3, 4, and 5, the sample variance of the residual is actually an unbiased estimate of the variance in the variance of the unobserved in the population. Okay. Again, why do we need assumption 1 until assumptions 5? We need those assumptions because given the assumption, we can use the sample variance of the residual. Any question from this? So a lot of the things that I've said in the past couple of slides have been really about statistics. Okay. So please take some time to recall your statistics course, especially to talk about sampling distribution, unbiased estimator, and then unbiased estimator or variance in particular. Okay. Any questions, any clarification? Okay, so don't worry. So for econometrics, there are things that are quite, intuitive. The discussions that we had in the early part of the lecture is quite intuitive in the sense that, okay, you understand the dependent variable, independent variable, and then the unobservables and stuff like that. However, we also have to know the technical sides of the econometrics to ensure that, the basic idea and the basic, like the general understanding of the econometrics has to be complemented with, the statistical and the mathematical sides of the equation, okay? So don't worry if you get lost, just try to read it. Now, if you have the sample variance of the residuals, then the square root of the sample variance of the residuals is going to be called the standard error, okay? And so not only that we want to estimate beta 1 hat, but we also want to estimate the standard error of the beta 1 hat. So the standard error of the beta 1 hat is just the square root of the variance of the beta 1 hat, okay? So what does the standard error actually measure? It actually measures how precisely the regression coefficients are estimated, okay? The smaller your standard error, okay, the more precise the regression coefficients, the larger the variance, then the lower precision, okay? So high standard error means lower precision, okay? And then low standard error of beta 1 hat, it means higher precision. Okay, so it's ideal for us to get a lower standard error because it means that we get a higher precision, okay? Okay, so I'm going to go back to Stata, and then in Stata, I'm going to show you that not only that we care about estimating the coefficient, okay, so this one is beta 0 hat, and this one is actually beta 1 hat. But we also care about estimating the standard errors, okay? So we care about estimating the standard errors of beta 1 hat, okay, which is this 0.527. We also care about estimating the standard error of the beta 0 hat, okay? All right, any questions while I go back to Stata and provide you with example of the estimation?
Hello, sir.
Yes, go ahead.
I have one question. So earlier you mentioned about standard error, but I still couldn't understand why do we need to calculate standard error to measure the precision of the regression coefficients instead of using the variances of the OLS estimators itself.
The variances of the OLS estimator. Okay, so why do we use standard error instead of the variance? So in general, we don't know the value of the variance. Okay, so sigma square is something that we don't know. We don't know the value of sigma square. So since we don't know the value of the sigma square, then what we want to do is that we want to try to estimate sigma square using the data. Now, the estimate of sigma square using the data is called the sample variance of the residuals. Okay. Now, we're going to use that to calculate the variance of beta 1 hat, and the square root of the variance of the beta 1 hat is going to be called the standard error. Now, why do we want to know the standard error or the precision of the estimate? Because at the end of the day, what we're going to do is hypothesis testing. Okay, we want to specifically test whether the estimated coefficient that we get is statistically significant or not. What does it mean to be statistically significant? It means that it's different to 0. Okay, Now, that's something that we're going to discuss in a couple of meetings in chapter 4, but that's the idea of knowing the standard error. So if you have a very high precision, then you're more likely to be confident that your estimate is the estimated coefficient that you get from the regression. Okay, but if the sampling variability or the precision is actually quite low, then you're going to face an issue. You're going to face an issue in terms of whether the estimated coefficient is actually close to the kind of like true value of the parameter. Okay, something that we're going to discuss in a couple of weeks or time. Okay, all right. One more clarification before I move on to Stata. Okay, so I'm going to go back to the previous Stata example that that we did. Again, just to recall the regression, what we did was that we regress salary on the return on equity. Now, the good thing about Stata is that you don't have to code or use the full syntax. You can actually use abbreviation of the syntax. So in this particular case, instead of just writing regress, you can just write reg. Okay, so reg salary ROE means that you regress salary on return on equity. Okay. Now, after we do the regression, which is quite fast, even with 200 observations, actually Stata can do very fast estimation given a high number of data. So you can do estimation of a data set with 1 million observation in probably seconds. Okay. All right. So again, I just want to note that not only that we care about the estimated coefficient, we also care about the standard error. Okay. Now, again, why do we need to know the standard error? Later on, we need to know the standard error when we do the hypothesis testing. Okay. All right. So I guess this is going to be kind of like a very simple depiction on regression. So I encourage you guys to do some regression on the software that you like to use. You can use Stata, you can use R, or if you still if you want to do SPSS or eFuse, that's also fine. But the idea is that you start to try to train yourself into doing regressions. Okay, first writing the model and then making sense of the model. Okay, so and then train yourself on whether the model that you have actually allows you to identify a causal effect of X on Y, or if it fails the assumption, particularly the zero conditional mean assumption, what are the consequences? Okay, of course, the consequences is that we're going to get a bias estimate. And then in chapter 3, we're going to understand more about the sign of the bias. Is it a positive bias? Is it a negative bias? That's something we're also going to discuss. Another thing that I encourage you to do is that working with data will allow you to get a sense on the correlation of the data and so on and so forth. Okay, so actually just doing regression probably is not the way of doing things. And the way that we usually do it is that we do a graphical analysis between variable Y and variable X. We looked at their correlation coefficient. We look at the scatter diagram and so on. So I provided you with sample codes in ELOC, and then in the sample codes you'll be able to actually get some ideas on how you want to do the analysis. You start with scatter diagrams, and then you probably want to do a coefficient correlation, and then after that you do the regression and do the interpretation. Okay. So it usually takes step by step, but since the class is quite limited to discussions of theories, then I guess the tutorial is also going to provide you with some insights on how to do regression in Stata. Okay, so I'm going to stop there and let you go. Otherwise, unless you have any questions.
Excuse me, sir.
Yes, go ahead.
I just would like to clarify on the softwares that we could use for statistical analysis. I haven't heard whether we can use Python or not for conducting the analysis, but yeah, I just would like to confirm on that.
Yeah, sure. Yes, you can do. You can use Python if you wanna, do the regression. It'll be more challenging in the sense that Stata is really optimized for you guys to do regression, cross-section, panel data, and time series. If-use is probably tailored for you to do estimation of time series data. It's going to be a bit more complicated, but if you want to do it in Python, I think it's good in the sense that it's going to provide you with some technical insights on regression. Okay, so you'll be able to get insights on the nooks and crannies of doing OLS, which is good for exercises. Okay, but again, you have to really balance between the technical aspects of the regression and the theoretical aspects of the regression. So if you can balance that, I think that's going to be awesome. Okay, and I think Python is also going to provide you with a basic knowledge of coding, and basic knowledge of coding goes a long way. Okay, so it's going to be very beneficial not only for this course, but it's actually going to build a foundation for future courses. Okay, because I think for the fields of economics and the fields of business, particularly with the strong, robust, and fast machines that we have, and the availability of data, I think more coding and then more technical analysis, will be done in the future. So it's good to respond to the idea. Okay.
Yes, sir.
I guess one last question before I let you guys go. All right. Thank you. I think you guys did very well today. So let's reconvene next week. Just recall that you have problem sets to do. You also have quizzes to do, and also please attend any tutorials that is going to be held by Helga. She's going to provide you with some insights on some of the difficulties that you face, and also provide you with some insights on the software side of things. Okay, have a good afternoon, and I'll see you guys next week. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.